First law of thermodynamics. So thermodynamics is 热力学。And thermodynamic process. And there will be 4 of them that we'll study and review, okay? So this is the review of this 2. Okay, so first of all, the formula, 1, what formula will be used? So there will be U, delta U is equal to Q plus W. So that's first one. This is the first law of thermodynamics. And the second one that we'll be using is work done by work done to, or work done by, right? It's equal to P times delta V. Okay, and this is coming from the F times D still. Okay, we'll show that. And the third one is the PV equal to nRT, so that you will also need to get involved with that. And number 4 that you will be using would be U is equal to 3/2 and the total number of particle times K, the Boltzmann constant, times T, which is also equal to 3/2, the number of mole N, and then R, the universal gas, ideal gas constant, and then times T. So those are the four formula that you will be involving here. And let's see how we will use them together. Okay, so just keep in mind this has to be absolute, meaning it has to be in degree K, and this R here depends on the circumstances. It's 8.314, right? And this would be the unit of joule, and then divide by degree K, and then number of mole. And so this Q and W, so Q will be positive, and W will be positive when it's to the system, the way we wrote it. So whenever it's to the system, so when it's by the system, then there will be negative. In this case, this is like you have a piston, and there's a force that you push, and if you move the distance of D, and your area here is A, so then the force is equal to P times A to begin with, right? And the work done is equal to F times D, so then that's equal to P times A times D, and A times D right here is equal to your delta V right there. This is the delta V, so that's equal to P delta V. So in this case, it's work done to the system, so this is, we define that as positive. So you can see if delta V is equal to 0, the work will be equal to 0. Okay? And this is called the ideal gas law. And this is the first law of thermodynamics. All right, so number 2, we're going to talk about the thermodynamic process. And there are 4 of them. So first one we're going to go through is delta T equal to 0, which is also called, so I'm going to say A, which is also called isothermal. So iso means the same. And thermal means, in this case, means temperature here. So it means T1 equal to T2 equal to T3, and it's always equal to constant. So delta T is equal to 0. And so in this case, delta T is equal to 0. And since U is equal to 3/2 N KT. So if N doesn't change, if N, the number of particle number of molecule or particle, if this is fixed, right? So when T doesn't change, that means this one here means T is constant. So then U must be constant. So U is also constant. Because N is fixed, T is fixed, K is just a constant, and K here is the Boltzmann constant. And so that's equal to constant, so that also means that delta U is equal to 0. So when delta T equal to 0, we are arriving at a condition delta U is equal to 0. Okay. And let me change the color here. So the curve for the delta, for the isothermal, it will look like this. And this is P, this is V. So if we draw another one, this one here means T2, and this one here means T1. So on this curve, every single point is T1. On this point, every single point is point. On this point, every single one is T2. Every single one is T2. But the two curve means T2 is larger than T1. And the reason is, if you draw a line right there, if you draw a line like this, for the same pressure, your volume at this point is larger than that one. So volume is larger according to PV equal to nRT. P the same, volume increase, so this one increase, so then T must increase. Okay? All right, so that's the isothermal. So now we're going to talk about the next one, which is adiabatic. So B, right? Adiabatic. Adiabatics means Q is equal to 0. So that's the definition of it. Q is equal to 0. So in that case, then you have delta U is equal to Q is equal to 0. So Q goes away. So then just equal to W. So then that becomes your formula right there that you can use. In this case, the adiabatic compared to the isothermal, it goes like this. Let's say you start with the same point right there. Isothermal goes more like that. Sorry, I want to draw more like this one here. Isothermal is like that. So this one's isothermal, delta T equal to 0. And this one here is adiabatic, Q equal to 0. So it will arrive at the lower point. So the curvature will be more like this, and curvature will be like this. So the relationship of adiabatic isothermal, right, will be like that. And this is P, and this is V. So what else do we know? Q equal to 0, so that's good to know, right? And so and the C is isochoric. So isochoric is also called isovolumetric. So that means the delta V is equal to 0, because iso is the same, and this means 并容. 容是容积, right? 容 it means volume, right? Okay. So delta V equal to 0, and so then we have this one here then tell us that W must be equal to 0 because this is equal to P delta V. So that's equal to 0. So then your first law now drop, reduce to delta U, and that's equal to 0, so equal to Q now. So then you can use this one here for your isochoric or isovolumetric. And for D is isobaric. So isobaric here, this means 定压 in Chinese. Right. So this is baric coming from the word barometer. Okay. So 定压, right? So then your work is equal to P, right? So P will be constant, and then times delta V. So now your first law, you can then write it as delta U is equal to Q plus P delta V. So that will be a relationship that you can count on, okay? And plus that you have this one here is constant pressure, so that you have P is equal to constant, and P is equal to nRT divided by V. So then T over V is also constant. If N is constant, of course. This one here, we treat that one as fixed, number of mole. And so then this means the T1 over V1 is equal to T2 over V2. So that is another relationship. So you have this two relationship to count on in the isobaric. In the isovolumetric, let's extend the ideal gas law. So in this case, means V is constant. So then you have nRT divided by P. And let's assume this is fixed. So then that means that T over P is constant. So then T1 over P1 is equal to T2 over P2. So that is for the isovolumetric. Okay, right. So that's all we're going to review here for thermodynamic processes. But let's look at another one, which is the work. So the work, this is P and that's V. So if we have something like this, for example, so that means V is increasing. So V goes from V1 to V2. So then delta V is equal to V2 minus V1. Okay? But in this case, it's doing the work to the outside. So by the system, this is by the system. So by the system, we define the delta V, the work is less than 0. So even though this is kind of contradictory, so we kind of need to treat this as negative. So the W here, it's equal to the area in terms of magnitude. So this is your W right there. That's your W, okay? So the W is equal to P delta V, which is a little bit of a contradictory here, but you got to keep in mind, since W is less than 0, so we're going to treat this one here, the delta V, we need to rewrite this one as actually V1 minus V2 here, okay? So then this will be less than 0. So P is positive and delta V is negative. So then we'll make this one negative. So that's just sign convention. It's a little confusing, but we have to give up something. Okay? And so if we have another case for the work, so this is P and this is V. So let's say if you have 3 steps like that. This is 1, this is 2, and this is 3. So you go from 1 to 2, and then 2 to 3, and then 3 back to 1. Okay, so in this case, this one here, 1 to 2, the work is equal to 0 because this is isochoric, right? That's isochoric. And 2 to 3, the work, this is doing by the system. This is by the system from 2 to 3. 2 to 3, it's by the system. So that's negative, okay? So this one here is the work from 2 to 3, okay? So 2 to 3 is the area there, right? It's called this is the W23. So W23, but it's negative. This is negative. And then we have 3 to 1, which is volume reducing from V3 to V1 volume reduced. So it's to the system. This one here is to the system here from 3 to 1. 3 to 1 is to the system. So then 3 to 1 is to the system, so it's positive. So W3 to 1, this is positive. So you can see this area here will be this one here. Will be, let me change color to blue. So this area will be this one here. So that's your work right there. Okay, so then this work, this 2 pieces cancel out. So from 1 to 2, 2 to 3, 3 to 1, together, the work done is this area here. And since this area, the blue is larger than the black, so altogether it's going to be positive. The work done, total work, right, is going to be positive. Because this one here is positive, and the area is bigger than this one here, W23, which is the smaller rectangle. So altogether, this W will be positive. Okay? Yeah. So I think that's all the important things that okay, we're going to talk about one more terminology here before we go. So if we have something that's go like this, P and V. So we're going to say from here to here, if this is delta T equal to 0, and that's going this way, so 1 to 2, this is called isothermal expansion. So that's a good terminology to know. Isothermal expansion. From 1 to 2. And if you're going from 2 to 1, 2 to 1, now it's going the other way now. 2 to 1, right? It's going this way. So 2 to 1, this is called isothermal compression. Okay? So isothermal expansion is by the system. This one is by the system. The work done is by the system because the volume increase. So this one work is, but by the system is less than 0. And this one here is compression, so the volume shrinks. So that means it's surrounding doing work to the system. This is to the system. The work is to system. So this one is positive. Okay? So this is isothermal expansion, isothermal compression. And now we're going to talk about adiabatic expansion and adiabatic compression. So very similarly to what we just described up there. So now instead of this, we will have something like this. The idea is the same. Idea is the same. So I said this is 1 to 3, right? So 1 to 3 is adiabatic expansion. And the work here, because it's by the system, so it's less than 0. And 3 to 1, it's adiabatic compression. So this is to the system, so the work here is positive. All right, I think that's all we're going to review here. And then until next time, keep learning physics. Bye-bye now.